When you work with DC circuits, the current that flows in the circuit is always going to be dependent on the resistance that the circuit itself can see. Today we're going to deal with series resistance. I have put two ammeters onto the circuit itself. There's an ammeter which is going to measure the current going in that direction from positive to negative, and there is another ammeter which is going to measure the current in that direction going down to the ground. Now I've only put those in so that you can see that the current which flows in is going to be exactly the same as the current that flows out. In this instance, the total resistance as seen by the power supply is going to be equal to 50 ohms. And so we can use Ohm's law to calculate what the current flow is going to be, and that's going to be the voltage divided by the total resistance which it sees. In this case, that's going to be 24 volts divided by 50 ohms, and that should give us a current flow of 0.48 of an amp. And I'm going to quickly call up my simulator and show you that is exactly what it does determine. On the simulator, you can see reference to PR1, the current, which is the current going in, and PR2, which is the current going out. They're identical to each other, and it's going to determine a value of 0.48 of an amp. Now, what if we were to add additional resistors into the circuit? Let's go and put in another 50 ohms over there and another 50 ohms over there and see what the simulator is then going to do. This is the revised circuit. In this case, we're going to say that the total resistance, RT, is going to be calculated as resistance 1 plus resistance 2 plus resistance 3, which is going to be 50 ohms plus 50 ohms plus 50 ohms, and that is going to give me 150 ohms as a total resistance. Now the current that's going to flow through the circuit is going to be the voltage divided by the total resistance that it can see, which is going to be 24 volts divided by 150 ohms. And if you do go and do that calculation, you get a value of 0.16 amps. So we should see 0.16 amps flowing in, and we should see 0.16 amps flowing out. And there you do have the simulation on the screen. And if you look at the top left-hand side, you can see that the current flowing in is the same as the current flowing out. And that's going to have a value of 0.16 amps. So in a nutshell, if you are dealing with DC circuits and you have got resistors, if you were to put resistors in series, you're going to be increasing the resistance, and therefore you're going to be decreasing the amount of current that's going to flow through the circuit. So for series resistance, all that you have to do is just go and add the values of the resistors together. When you start to put resistors in parallel with each other, you create a greater amount of paths for the current to flow. So theoretically, you're going to find that depending on the resistance that you are going to use, you could actually have the flow of current that's going to go up, because the total resistance that the circuit is going to see is physically going to be less. Let's go and do a couple of calculations just to prove this to you. On the screen, we have got a single resistance that can be seen by the circuit. So the total resistance seen by the circuit is going to be 50 ohms. The current is going to be the voltage divided by the total resistance, which in this case is going to be 24 volts divided by 50 ohms. And if you go and do the calculation itself, we should get a value of 0.48 of an amp. And let's go and see whether the simulator gives us that value. And that is it. You can see that the current going in and the current going out is going to be exactly the same. We're going to have one value that's going to come out. Maybe I should take away that ammeter. No, I'll still leave it there for a while. So on the screen in front of you, you can see that we have introduced a second resistor, also 50 ohms, which is in parallel with the first resistance. Now, what is the resistance that's going to be seen by the circuit itself? The resistance parallel, if you've just got two resistors, is going to be resistor 1 times resistor 2 over resistor 1 plus resistor 2. And that becomes a value of 50 times 50, divided by 50 plus 50. And if you do go and do that calculation, your parallel resistance is actually going to work out to half of the resistance that you can see for a single resistance. So in this case, it's going to calculate out as 25 ohms. Now we can say that the total current that's going to flow through the circuit is going to be the voltage divided by the total resistance that the circuit can see, which is going to be 24 divided by 25. And in this case, it's going to give us a current of 0.96 amps. So compared to the calculation on the left-hand side, you can see that we are going to have twice the amount of current that is going to flow. Let's go and see what this does on the simulator. And that is exactly what we are seeing on the simulator. The current that flows in, which is the same as the current that flows out, is now going to have a value of 0.96 amps. So effectively, there's an extra path to take the current through it. And therefore, the total resistance that is seen by the power supply is going to be of such a nature that we can allow more current to go and flow through the circuit. Right, I am now starting to run out of space, but I'm going to do this as best as we can. Whenever you have 3 or more resistors in parallel, then there's a different equation that I'm going to go and use. I'm going to say that 1 over resistance parallel is equal to 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. And if you had more resistances than that, then plus 1 over resistor 4 plus 1 over resistor 5. So in this case, 1 over resistance parallel is going to be 1 over, what is number 1? It's going to be 50 plus 1 over 50 plus 1 over 50. And just for the sake of convenience, I've gone and put them as all the same values. You can go and try out different values. Now I need to have a common denominator that all of those numbers can go into, and they can all go into the number 50. 50 goes into 50 once, multiplied by the number at the top, which is going to be 1, plus the next 50 goes into it once, multiplied by the number at the top, which is going to be 1, plus the next 50 goes into it once, multiplied by the number above it, which is going to be 1, and that would give it. So 1 over resistance parallel is going to be equal to 1 plus 1 plus 1 is 3 over 50. And therefore we can say that resistance parallel is going to be the inverse of that, which is going to be 50 divided by 3, and 50 divided by 3 is going to give me 16.67 ohms. I'm going to take away all of the clutter so that I can do the rest of the calculation. I'm just going to move that equation upwards. So in effect, the total resistance that can be seen by the circuit is going to be 16.67 ohms. And maybe let's just go fix that up. It looks like it's a bit of an error. Great, I've just rewritten that value. I had 16.77 instead of 16.67. So the total resistance seen by the circuit is going to be 16.7. Now let's go and calculate what the current should be through this circuit. The current is going to be the voltage divided by the parallel resistance, which in this case is going to be 24 volts divided by the 16.67. And if I do my calculations quickly, I'm going to get a value of 1.44 amps. Total current is going to be 1.44 amps. Let's go and see what the simulator gives us. And indeed, that is exactly the case. So you can see that the current which is going to flow through the total circuit is going to have a value of 1.44 amps. So the more resistors that we've put in parallel with the first one, the more alternate paths we're going to allow for a flow of current to take place. Now, I actually should be calculating the current that flows through each of those resistors, but I'm going to save that for a later video where we are going to do the Kirchhoff's current laws. And that completes our little exercise dealing with resistors in parallel in a DC circuit. As always, if you do come onto my workshops, it could be in my classes, we will go and do these calculations a lot more in depth and give you lots of opportunity to do it yourself.